Hi, my name is Shenhui Yang. I work for Wolfram Alpha team localization, mainly working on the translation and the scientific content for Wolfram Alpha. My talk would be on some of my hobby project to using Wolfram language to solve problems. It's called the art of problem solving in Wolfram language in 2022. There will be 4 interesting problems in the talk. Hopefully you will enjoy them.
The main theme is the art of problem solving with Wolfram language. I have done 2 similar sessions in 2021 and the year before that. So it was they were published on YouTube and the Wolfram channel, and lots of people like it. So I'm going to continue doing that thing and solve 4 problems and with the Wolfram language in 4 different branches of the mathematics. It's just like international math Olympiad style. You have geometry, algebra, combinatorics, and a number theory. So we are going to solve 4 very challenging problems in a very short time. So let's begin. And you will see how Wolfram language helps you to deeply understand the mechanism behind those difficult problems. The first problems we are going to talk is from the Ingenious mathematical problem and the method. It's a very tiny book. It's very cheap on Amazon, but it's a problem collection book with a lot of interesting mathematics and some physics problems. And interestingly, I find a piece of history. So this is the guy who proposed the problem on the book. So you can find his photo on eBay somehow. It's very surprising to me. So the problem is quite interesting. It's about a shingle. Shingle is like a tile on your roof. You know, it's on an inclined roof. The problem states like this. You have a piece of metal shingle on your roof. Okay. So it's smooth, but the smooth means we don't have bumps, but you still have friction on that. So there's a dynamic coefficient of friction is 0.5. So the problem is quite interesting is that you have a piece of shingle sitting on the roof without pushing it, just by having, you know, it going through a thermal expansion and thermal extraction contraction cycle. The shingle is actually going to move along the roof and going downward. So this is a problem's quite fascinating. If you don't think about it deeply, you probably feel like why it just moves without pushing it. So the key idea is you should think about a shingle on the flat surface and it go through a thermal cycle. So if it expand and contract, so you think about there should be a fixed point in the shingle because it's on the flat surface. So the thing in the middle should not move. So if you incline, put the shingle on the inclined surface, because we just changed a little bit. So what it means is the fixed point of that shingle actually move slightly off the center. So let's have an illustration of that thing is just say you have this shingle go through a thermal expansion process. So let's say it just have a fixed point along somewhere in the within the shingle. And let's think about the process for expansion. So once it grows longer, everything moves except the fixed point. So because this thing moves along the, the thing expand along the roof, so all the friction should go this way because think about it, it moves this way, right? The friction just points inward. And now you can just use a very simple force analysis and assume the fixed point is at a piece of wall. So if you have a friction go this way, so it means everything beneath the fixed point actually push toward the wall, and everything above pushes downward. So you can just set up very simple force because everything moves really slowly. So you can think about everything is under a balanced force situation. So in this case, N represents a force that's exerted from the fixed point. Like think about a wall to the all the pieces with a lambda length. And you just set up the force balance equation for the piece that's below the fixed point and above the fixed point. And then you can just, you put everything into the solve equations, and it would give you the location of the fixed point and the force exerted on the fixed point. And I think about a virtual wall there. So the material is already uploaded on Pathable. So if you want to take a deeper look at it, you can just review the notebook afterwards. But this is just how you think about to solve this problem. And on the other side is during a contraction process. So everything is just the reverse process of the expansion process. You can again compute the location of the fixed point in this process. It happens to be that if the parameters are the same, the two equation differs only by replacing lambda to 1 minus lambda. So what it means is, say the fixed point is around like 80% of the for example, is like 80% of the whole length. In the other way is it just moves to the opposite, just to reflect that point with respect to the midpoint of the shingle. So you can just compute that again, and you will have basically the same result just by replacing lambda with 1 minus lambda. And then you compute the entire expansion just by compute how the midpoint shifted away from the fixed point. You do that twice, and eventually you will have the result. So this is just a very quick sketch of the entire analysis of this problem. And in short, we can say that in the expansion process, because the fixed point is somewhere above the center point, so the center point is actually pushed down. And in the contraction process is because the fixed point is somewhere below the midpoint, so it pulls the center of shingle downward. So eventually, all the displacement that you have is just a summation of these two displacement. And you add them up to give you a result is like 2 milli-inches every day go through the thermal cycle, okay? And what Wolfram Language helps us to understand deeper about the problem is, if we go through all the solving equation stuff, what we have left is expression about the lambda in terms of the mu and the theta. Theta is the inclination, and the mu is the coefficient of friction. Because lambda determines the eventual displacement of the shingle. So if we have constant lambda, we should have a constant displacement for the shingle during a thermal cycle. What is very important in this type of thinking is in engineering, we always want to fix one variable and change a bunch of others. So in terms of fixing the lambda, which also means fixing the constant shift of the shingle, we are looking at the contour that every line means the constant movement, and how can we change the inclination and the friction coefficient to make it happen. So this is just a very common and important idea in engineering. We use a contour plot to measure this kind of a family of curves. And this is very easily be done in Wolfram Language. You just use contour plot to make it happen. And it gives you a very beautiful plot about the mechanics behind this type of thermal expansion, okay? Okay, this is the first problem. The second one is actually looks very beautiful. It's from a Japanese temple geometry problem, Sengaku problem. Also, we have someone from Canada. This is also a problem mentioned in the CRUX Mathematical magazine from Canada. So the setup is really simple. So you have a fixed circle and you have a fixed chord, okay? And you have the chord is the blue line, and the large circle is the fixed circle. Okay, you have a point, a blue point on the blue line, and it moves it around. And every time you move around, you basically draw a circle tangent to this point and tangent to this chord at this blue point. And you have a larger circle also tangent to the point. So the key is, regardless how you move the tangent location and the circle, changes size, but their ratio is the same. The radius of the ratio of the radius of the two circles are the same. So this problem is usually very difficult to solve if you don't have a proper tool to handle that. The tool we have here is already, I have contributed that to Wolfram Function Repository a while ago. It's called a circle inversion. It's a sister function of a curve, inversion curve. But this one is give you a lot more syntactic sugar to handle this type of problem. It's called Abello type. So usually if you have like a circle, tangent circle, and you have some, chord line intersect to the point, arc. So you want to take the inversion of that point. So let me just quickly show you what inversion looks like by definition. It's basically a simple idea from sort of a middle school math. It's called a circle power. So you can read that in math board. And also the help function for circle inversion include lots of examples for you to play around and to understand what's behind that. So assuming you have some idea of that thing, so the key to prove that is we choose the inversion center on the large black dot here. So let's just move that to the inverted space. So inversion just change circle to circle or circle to line sometimes, and the entire thing is usually the line. If the line of the go through the inversion center, it just will be invert to the line itself. So I've sketched a very quick proof underneath, so you can quickly take a look at it. It's just using a Pythagorean theorem twice on the triangle above and below the chord. So you do that again, and typically this formula is also mentioned in the help document for the circle inversion. You will see clearly why how the original circle is inverted to a new circle here. But the idea here is once you do the inversion, so let's go back to the original circle diagram. So if we change the relative position between the chord and the circle, you see the ratio changes, but it's fixed, for the point on the tangent point along the chord. So if we take a look at the inversion version of that, is you move the tangent point, so the tangent the size of the circle changes this way, because these two things just like homotheity, linear projection of each other. So regardless how you move that, it of course stayed the same in shape, stays the same in the ratio of the radii would be stay the same. But what happens if we change the chord line, the relative location between the chord line and the larger circle? So in the inversion space, it just tilts the line. So it just show you the relation between the two very clearly. So if say we fix the tilt angle of the new line, of course you move that, it's the same. It only depends on how this line is inclined. Okay, the proof is sketched here. So if you want to just do the simple math by yourself, you should be able to handle that if you attended to this lecture, right? I think everyone should be good enough to do that. Okay, let's move on to the third problem. That's why I like to include the 4 problems, and then I don't really expect everyone, from fresh to grab everything, but I just want to show you how powerful this language is, because now you have sort of like simple physics, and then you have like inversions like Euclidean geometry and sort of Poincare. Inversion is actually related to Poincare stuff, and I'm going to show you quickly how it's applied to a more advanced problem, because in Wolfram language you can just do all branches of math very quickly in one interface. Okay, this one is originally very fundamental question from Fermat-Little theorem. Okay, if anyone need to recall the theorem, it's just you can just search that on Wolfram alpha. So basically, it's say, for example, if you have a prime 31. So for every number, because it's modular space, so every number means just 1 to 30. 0 is kind of trivial because it's multiple of 31. So for every number from 1 to 30, regardless which one you pick, you take the power of that p minus 1, that's to the power 30. You always have one modular p, or it's minus 1 is a multiple of 30. So there's some number are kind of strange because, for example, you have a equal to 1. So you guarantee that a square equal to 1, right? But it's not the other way around. If you have a square equal to 1, a is not necessary 1. Sometimes it can be minus 1. So the simple, the same idea is here. For some of the numbers, you take 3 to the power of 1, power 2, power 3, and go through entire list of 30 numbers. Eventually it goes to 1. But some number are not. For example, 4 to the power of 5, you already have 1 here. So that means some of the multipliers, the base of the exponential are not equal, right? So what you do here is you actually take a look at it just by the simple calculation. You can just find, okay, we have a 3 as a primitive root, which means you must have 3 to the power of 30 to get a 1 modular 31. Okay, but he's not alone. You have some other friends here, so that you can take a primitive root list and it generate a bunch of numbers that satisfy this one. And also, there's a very interesting function in function repository. It's fraction mod. It also shows you some example why 4 is not, because you take the 4. 1 over 4. What's the model number of 1 over 4 mod 31? It's just to find number x such that 4 times x is 31. Is 1 mod 31. Just the remainder is 1 if you divide it by 31. So this is quite clear that this one is 8. 8 is 4 to the power of 4. So 4 times 8 is 32. 32 is 1 mod 31. So it divides 31 by, and then we have 1 remain. So this gives you an idea about how to find the fraction mod. And so this is just some simple calculation. But how do we, understand a little bit more about that? So I think the graph ability in Wolfram language is now very powerful. So you do that thing for the, say, for example, 3 to the power of 1 to the power of 2. It looks like, it's not trivial because you first have everything left from 1 to 30, but also it's just a rearrange of the numbers, right? It's a rearranger of the numbers. So it probably associated with some very critical way to permute the number from 1 to 30. So I'm not going to the theory, but you can play around it. So one of them is use the weakly connected components based on the graph, because all the graph is basically 1 to, let's say, 3. You map power. So you map the power to the eventual remainder. So 3 to the power of 1 is 3, and 2 is 9, and so on. So you have 1 to 30 and map to a rearrangement. So eventually you can use this type of things to extract the closed cycles, the little cycles in the entire permutation. And you can use this function to do that, just to take out the things in the subgraphs and to check out the cycles. This is also discussed in my talk last year, so you can check on the YouTube to see related modular dynamics associated with a graph. But sometimes we want to see, this is what I call is you have airports here, right? Like Champaign Airport, Chicago O'Hare. The points are fixed, and the permutation is called permutation crazy airlines. This is how it connects all the points after it permutes. So if you want to highlight some of the subgraphs inside, so this is what you do. It's very simple. You just use a highlight graph, and this is what you have. And all the buttons are the subcycles. Then you can play around to highlight the subgraph. This one is based on the Poincare curve, Poincare arc. I found on Stack Exchange. I just modified a function to enhance the orientation of the arc, because the original one, it does not give you the orientation of the arc. We needed that because the thing about this arc, it's not a guarantee. Sometimes it go to the complementary arc, goes to other one, or just go outside of the circle. So in this way, you can just manipulate the permutation and study that. You can also change the root, this base, because we have a bunch of friends here, So you can just change it to 11, 12, 13, 17, and play around. You will find, you can take a look at it. At least it's visually pleasing, to see the type of graph and associated with permutation based on the primitive roots. It just boosts your understanding to this type of simple math theory, number theory stuff into advanced like group theory, category theory, everything you want in future. You can start from the primitive roots and other number theory stuff, combining with the graph theory stuff, okay? Good. So I think it's just very important, very pleasing stuff. And built upon these graph stuff, Wolfram language, I think after 13, we moved to tree. So this is the last problem from a very challenging book by Stanley. It's I think it's the version 1. I checked the version 2 of the Enumerative Combinatorics. This problem, this topic is just not there. So this is a very strong tree capability in the Wolfram language. So this is not exactly a problem, but it's a sort of a theorem or example discussed in the version 1 of the volume 1 in this book. It's on page 23 to 24. So this is a typical graph. Let's first just talk about example. This is exactly the same example in the book. It's 1, 2, 3, 4, 5, 8 permuted to 5, 7, 3, 1, 6, 2, 8, 4. So how you construct the tree based on his example is you can construct a tree in many ways, but this one is a kind of, I think it's called an increasing tree or something. So the root is always the least item. For example, the root is 1 here. You have a list. All right, because the permutation, it always starts 1. Sometimes you can do 0, but in Wolfram language, it always starts from 1. So 1 is by definition should always be the root of entire tree. Okay, and you build a tree recursively. Let me just give you an improper way to do that. Is you think about it is you chop off a limb and attach your elbow to the joint here. So this way is basically you find the least item in the tree, in the list or in the permutation. You make it the root, and then you split into the left and the right part. It's you have 5, 7, 3 and 6, 2, 8, 4. So make these two things as the subtrees, and then you do that again for the subtrees. For example, 5, 7, 3. The least item is 3. Okay, you make it a tree, and you make it a root for the subtree, and you do that for 5, 7 again. So on the right hand side, 2 is the least one. So think about the 2 is somewhere in the elbow. You chop off a limb, you attach the elbow to your joint. So 2 is on the elbow. So it's kind of weird like this, you know. 6 is on the right-hand side of, on the left-hand side of 2 here. So you put a 6 on here, all right? And 8 for everything goes to the right-hand side of the tree of 2. And you do that for 4 and 8 again. So the key idea is you do that thing based on this short program. It looks tedious, but you know, the left-hand side thing and the right-hand side thing are exactly the same. So if you just set up the properly for the input parameter properly, you can do that recursively to build upon the tree. I think time up. Okay, yeah. Thanks for attending. Everything is uploaded on the cloud right now. So if you have a problem with that, we can discuss in the office hour. Thank you.